Okay, so related to statistical process control, we have several topics to discuss, and the statistical concepts, knowledge in statistical concepts is a necessity. And while we discuss this topic, that is the fundamentals of process control and process design and control. So let me first talk about the statistical concepts. There are certain other concepts you must first you must have an understanding before we go on discussing the control charting and all other the tools and techniques in statistical process control. Now, yesterday in the last class we mentioned about the measures of dispersion, and we discussed already the first two measures, that is the range and the variance or the standard deviation. The third one, that is the interquartile range, is also is used in many cases. So the interquartile range is essentially, we refer to the lower quartile, that is Q1. And how do you define Q1? Is the value such that 1/4 of the observations fall below 8 and 3/4 fall above it. So that is the definition of Q1. The middle quartile is the median. Half the observations fall below it and half above it. Similarly, we have the third quartile, that is the value such that the 3/4 of the observations fall below it and 1/4 above it. I think it's clear to you. So the interquartile range is given by IQR is Q3 minus Q1. So this is the traditional practice. To find the UQR, what you have to do, the data are to be ranked in ascending order. That is the first step. The first quartile is located at a rank of 0.25 into n plus 1, where n is the number of data points in the sample, say 100. Okay, so 100 is suppose the sample size. So the third quartile is located at rank 0.75 into n plus 1. Okay, so what is the first quartile? That means 0.25 n plus 1. And what is the third quartile? That is 0.75 n plus 1. So here in an example, so you have 20 observations. These are the values like 2.2, 2.5, 1.8 and so on. So how do you determine the location of Q1 and Q3? That is straight you are applying the formula, that is 0.25 into 21. 21 is n plus 1, 20 plus 1, that is 5.25, and similarly location of Q3 is 0.75 into 21, that is 15.75. So what do? That means you arrange the data in the ascending order. Is it okay? That means the first data point is 1.7 and the last one, that is the 20th one, that is 2.6. So at this location, that is 1.825, you have the value, that means the rank is 5.25. That means this is the rank, there is the fifth rank, between fifth rank and the sixth rank. So what is the quartile 1? That is 1.825. It's clear. And similarly, this is the location of Q3 is the rank is 15.75. That means almost it is near to 16. So the corresponding value we can compute, that is 2.275. So this simple rule we follow, and obviously now you can determine the interquartile range. Right, it is a measure of dispersion. So how do you do that? That means Q1 1.825 we have already measured, and Q3 is 2.275. So interquartile range is the difference, that is 0.45 millimeter. So this is the relative frequency, and this is versus the data value. So 25% is of the points, the data points are less than say Q1. And 75% of the data points are less than Q3. Is it okay? So this is interquartile range. Now we are referring to the probability distributions. There are you are supposed to use various kinds of tools and techniques, and these tools and techniques, many such tools and techniques being used in quality design and control, and are based on certain distributional assumption, right? We have already mentioned that you need to deal with the random variable, either discrete type or continuous type, in quality control and improvement purposes. So what you try to do, that means against a particular, say, random variable which you are dealing with in a given case, you must be aware of what kind of the probability distributions it may have. So now this just I will discuss briefly some of the important probability distributions and their characteristics which are commonly used in quality control and design. So these probability distributions are grouped under two categories. The first one is the discrete distribution. That means the corresponding say random variable is of discrete type. So these distributions deal with those random variables that can take on a finite or countably infinite number of variables. Essentially, they can assume the integer values. Several discrete distributions have applications in quality control, so I will just name them. Like the first one is the hypergeometric distribution. Okay, so the hypergeometric distribution, there's a lot of the applications. Okay, and particularly by an application related to, say, acceptance sampling, when you deal with isolated single lot. So the distributional assumption is hypergeometric. So hypergeometric, this is the probability mass function. This is the probability mass function, and you have so this is basically sigma, the px is given by dcx n minus d n minus x, and this is the expressions you use, and x could be, that means the number, okay, of is the number, like say when you deal with say the number of non-conforming units in a sample. So it may assume several any one of these integer values, and in n and d, that means this is n, not m, this is n into n comma d. So maximum could be n, and in the x values, and n is within, either it could be n or it could be d, between d and n. So this is the formula you use, and so the number of non-conforming items in the populations, the size of the population, capital N is the size of the population, small n is the size of the sample combination of d items taken at a time, and number of non-conforming items in the sample. Okay, so this is the hypergeometric distribution. So obviously what I am asking you to do, like say for any say the distribution you come across, there are parameters. So what will be the expression of these parameters, particularly mean and standard deviation. So that always you need to compute, like say given the probability mass functions for the hypergeometric distribution. So what will be the expression for the mean and the standard deviation. So that always you can compute. Similarly, we come across binomial distribution, and binomial distribution, this is NCX or NCR, p to the power r into 1 minus p to the power n power r. So the value of r could be 0, 1, 2 up to n. Is it okay? N is the sample size. Then in many cases we assume that that the random variable is Poisson distributed. So this is say the probability mass function for Poisson distribution, lambda to the power e to the power minus lambda power x into factorial x. This should be lambda to the power x by factorial x. Is it okay? Where lambda is equals to the mean or average number of events that happen over the specified product volume or the time period. Okay. Now, so these are the three distributions we come across frequently. One is the hypergeometric distribution. The second one is the binomial distribution, and the third one is the Poisson distribution. In many cases, what we do, you may go, under certain conditions, you may go for Poisson approximation to binomial distribution. Okay, so when we refer to these cases, we'll have these assumptions or these approximations. So later on, we'll take up numerical problems, and where in many cases you go for Poisson approximation for binomial distributions. As far as continuous distributions are concerned, we have many, but here at this point in time, I will be referring to the normal distributions. Okay. The most widely used distributions in the theory of statistical quality control is the normal distribution. So this is the probability density functions you are all aware of. So this is one, and there are two parameters we have. One is the sigma, and the second one is the mu. So these are the mu is the mean, and sigma is the standard deviation. So this is the typical, the distribution fx versus x, and this is a symmetric distribution, and with mean mu and the standard deviation sigma. Is it okay? It's okay. Now, what we try to do, that means we standardize the normal distributions, and we refer to the standard normal distributions, where x is transformed with z, and z is essentially is nothing but the difference of value of a particular value of the random variable from the mean, and this difference is expressed in the standard deviation units. So the difference is x minus mu. So mu is one of the parameters. So x minus mu, this difference expressed in the standard deviation units. So this way, the z has been defined, and so obviously the probability distribution function, probability density function, it's not distribution function, density function is phi z is 1 minus 2 e to the power minus z by 2. Is it okay? So where z may lie anywhere between minus infinity to plus infinity. So here obviously with this transformation, the normal distribution, we will have a mean of 0 and variance of 1. Is it okay? So normally this is specified as the z n 0 1, and we say that z has a standard normal distribution. Is it okay? So x is transformed into z. This is an example, just the simple examples I have taken. The length of a machine part is known to have a normal distribution with mean of 100 millimeter and the standard deviation of 2 mm. Is it okay? So what proportion of the parts will be above 103.3 mm? So what you need to do, let x denote the length of the part. So mu 100, sigma is equals to 2. So the standardized value of 103 and 3 corresponding to, say, x1 103.3 minus 100 divided by 2, because sigma is 2, and so it is 1.65. So what you refer to, that means area under the curve beyond 1.65. So this is the probability that z is greater than 1.65. So here it is 1.65. So if you refer to the standard normal table, okay, so you will find the area under the curve beyond z equals to 1.65 is 0.0495. That means 4.95% is the areas. Okay, so this way we calculate, we refer to the standard normal distribution. Okay, so what proportion of the output will be between 98.5 and 102? So what you try to do, against 98.5 you calculate corresponding Z1. Is it okay? When the mean and the standard deviation is known. So this is 1.00, and similarly against 98.5, what is this Z2? That means 98.5 minus 100 divided by 2, that means minus 0.75. So now what you try to do, that means area area under the curve, okay, between say z equals to 1.0 and z equals to minus 0.75. So, minus 0.75 is somewhere here, and 1.0 z equals to 1.0 is here. Is it okay? So, the area is this one. Is it okay? That you have to compute. So, the required you have to refer to the standard normal distribution, the corresponding table, and the required probability equals this 0.6147. So, is it okay? So, this value you get by referring to the standard normal distribution. Similarly, this area also you get, and when you subtract these two areas from 1, okay, so you get the value of 0.6147. It's clear? So, so you know how to use this standard normal distribution table. What proportion of the parts will be shorter than 96.5? So, that means against 96.5, again you calculate its z value, that is minus 1.75, okay, with reference to 100, that is the mean, and the standard deviation is 2. So, this area again you refer to the standard normal distribution table. So, against a value of z of minus 1.75, okay, so area under the curve beyond this value up to minus infinity, that is 0.0401. So, 0401, that means 4.01% of the points they will be shorter than 96.5, okay, or the parts. Okay, so these are the simple examples. Similarly, it is important not many of the parts exceed the desired length. Obviously, if a manager stipulates that no more than 5% of the part should be oversized, what specification limit should be recommended? So, here the problem is that x should be greater than equals to the probability is 0.05. So, this is 0.95 less than equals to a. So, corresponding is a z value, that is 1.645. So, that you get, and you need to determine x1. So, this is known, this is known, this is also given, and so what you need to do, what will be the corresponding value of x1. So, therefore, this way we say that this way you determine the value of x1, and we say that a should be set at 103.29 to achieve the desired stipulation. Is it okay? So, this is another example. Now, under continuous distributions, say exponential distribution also is used, and Weibull distribution, particularly when you try to model the reliability function of a component. And what is reliability? Reliability, as you know, this is one of the dimensions of the quality. So, this is the probability, the mass function, probability density function for the Weibull distribution, and this is exponential distribution is a particular case of Weibull distribution. So, Weibull distribution is having 3 parameters, that is the gamma is referred to as the location parameter, beta is the shape parameter, and alpha is scale parameters. Okay, so this we come across. Now, we also must have an idea about the sampling, because when you go for statistical process control through control charting. So, while you construct the control chart, what you need to do, that means from the process or from the population, you have to create a sample. So, obviously, while you create a sample, that means you must have a thorough idea about the sampling procedures. Okay. So, just I will be referring to the concepts, what is the basic concepts in sampling. So, a sampling design is a description of the procedure by which the observations in a sample are to be chosen. It's very simple. So, what is a simple random sample? One of the most widely used sampling designs in quality control is the simple random sample. So, random number tables, you refer to random number tables, or computer generated random numbers can be used to draw a simple random sample. What is the stratified random sample? Sometimes the population from which the samples are selected is heterogeneous. That means, suppose there is a in the population of the persons. So, there could be the male population, there could be female population. This is just one example. So, and you have to you have to collect the sample from the population. So, and it must be representative. So, what you try to do, that means you collect one sample from say the male population and another sample from the female population. So, this is just a simple example. So, this is referred to as a stratified random sample. Okay. So, for instance, consider the output from two operators who are known to differ greatly in their performance. Same example. So, you have to collect sample, that means from one operator, and similarly for the second operator. So, I will elaborate it later on. The stratified sampling method is widely used in the field of the quality control. Okay, so rather than randomly selecting a sample from their combined output, a random sample is selected from the output for the each operator. This way, both operators are fairly represented, so we can determine whether there are significant differences between them. Is it okay? So, whatever the quality characteristics you are referring to. So, a stratified random sample is obtained by separating the elements of the population into non-overlapping distinct groups called strata. Is it okay? Like one group is female, another group is the male. Is it okay? So, the data sets for one operator and the data sets for the second operator. So, these are called as the strata, and then selecting a simple random sample from each stratum. So, similarly, we have a cluster sample. Okay, the cluster is formed, and many a time you come across the situations the clusters are formed. Is it okay? So, many a time what you do, the entire population is grouped into several clusters based on certain the characteristics. So, if a plant has plants throughout the southern eastern United States, it may not be feasible to sample from each plant. Is it okay? So, it's like say, so cluster are then defined, say one for each plant, and some of the clusters are then randomly chosen, say 3 of the 5 clusters. Is it okay? So, this is the concept of sampling. Now, before I refer to certain fundamentals, of the statistical process control, the techniques. So, I am again referring to the prevention based quality control, this diagram. Is it okay? As I have already told you that say the first stage in the evolution of the quality system is inspection, and the next one is the quality control. So, whatever the statistical process control, what we are talking about, we assume that we are in a stage, in a condition where prevention based quality control is a necessity, and this control chart which you are going to use for statistical process control, obviously the system should be the prevention based quality control. So, what is it? That means you have several kinds of resources, you have the process, and then as a worker, as an operator of the process, what you need to do, that means you need to go for measuring the quality characteristics, and if adjustment you need to have in the measurements, you must be able to do the adjustments. Is it okay? And ultimately the output should be the acceptable to you, and so that you get a satisfied customer. So, this is in this prevention mode, prevention based quality control, the control chart is to be used. Now, I will just briefly tell you that why control charts, what is a control chart. So, what is a control chart? Control chart is a graphical tool for monitoring the activity of an ongoing process. So, it is an ongoing process. That means through control, by using control chart, what you can do, you can go for online real time control. Control charts are sometimes referred to as the Shewhart control chart, because Walter A. Shewhart, he actually the first way back in 1920s, he introduced the concept of control charting, and subsequently his concept of control charting was implemented in several well-known organizations throughout the world. Now, how do you construct a control chart? It's very simple. You have x-axis, you have the y-axis. Now, supposing for a given quality characteristic, you need to construct the control chart. So, what you try to do, you need to collect the values of the quality characteristics, okay, from the process. The values of the quality characteristics are plotted along the vertical axis, that means the y-axis, and the horizontal axis represents the samples or the subgroups. Okay, as I have already pointed out, that the samples which you draw from the population or from the process, there are certain rules, there are certain norms. Later on, we will discuss this one. So, and these the samples you have to draw as the process is on. That means the time order is to be mentioned. It means that if you say it's the first sample, that means the first sample is drawn first. If you say it's the second sample, that means the second sample is drawn next, like this. So, time order is to be mentioned. So, this the x-axis represents the samples from which the quality characteristic is found. That means instead of measuring all the units in the population, you just draw a sample, and within the sample you have a number of values, and those values are to be collected, and then you get its the average value. Okay, so say the average represents a particular sample quality characteristic. So, this average is calculated based on the number of observations in the sample, that means the sample size, and these characteristics are then plotted in order of time in which the samples are taken. This is the general way of constructing the control chart. So, it is very, very simple. So, examples of quality characteristics like average length, average diameter, average tensile strength, average resistance, and so on and so forth. Okay. So, this is the typical control chart. So, this is actually the y-axis, this is the x-axis, and in a typical control chart, you have a center line, and you have the upper control limit, you have the lower control limit. Is it okay? And usually they are at equal distance from, say, the center line. So, on one side you have the upper control limit, on the other side the same distance you place the lower control limits. Okay. Area between the upper, this point is to be noted, the area between the upper and the lower control limits, these reflects actually the natural variation of the process, whereas the area beyond UCL, that means this area, or the area beyond LCL, that means this area, this represents actually the variation due to assignable causes. That means if a certain sample point falls over here, you assume that there is a variation definitely, but this is within the natural variation. But if the point is somewhere here, that means against the fourth sample, that means you will find that there is a variation, because your target is center line. So, this much variation. Now, this variation is due to some assignable causes, and something has gone wrong at that point in time while you collect data for the fourth sample. So, this is referred to as the assignable cause. Okay. So, and whenever you find that the point is the plotted, says the fourth point is plotted, say outside, say here all the points are plotted within the control zone. So, you may assume that the necessary condition for in control state has been achieved. Okay. So, by using a control chart, you know whether the process is in control or the process has gone out of control. So, if a point the plots outside of the control zone, we assume we assume that the process has gone out of control. That means out of control state. And if you find that the point plots within the control region, that means the area specified by the upper control limit and lower control limit, we assume that the process is in control or is in control state. So, what are the benefits? When to take corrective action? Is it okay? So, as soon as you find that the process has gone out of control, now you have to take some corrective action so that the process is brought back to a state of control. Is it okay? So, from the out of control to in control state. Type of remedial action necessary, that means when you start using a control chart against a process, that means as you are continuously using this control chart, you know the behavior of the process, that means ins and outs of the process, you have a thorough knowledge, and so what kind of remedial action you need to take to bring the process back to the in control state, that you will come to know. When to leave a process alone, that means if you find that the process is continuing in control state, so in many cases you don't go for the controlling the process, you leave the process alone. So if you can create such a condition, you assume that my purpose of using a control chart is fulfilled. We'll be discussing the process capability, and when you start collecting data through control charting, later on this data you can use to the measure the capability of a process. Is it okay? So if you start using a control chart, so based on the information you collect, so you can measure the capability of the process. Possible means of quality improvement. Is it okay? So always you go for it. So there are two types of the variations. And what we have mentioned, that the two types of causes of variation, and what we have been stressing, that any exercise on quality is essentially an exercise on controlling the variability. And so you must know that the causes of variation, that there are two types of causes of variation. One is the common cause, is also referred to as the chance cause, you may note down, or the natural cause. Whereas the second kind of the causes, they are referred to as the special causes or assignable causes. So control of a process is achieved through the elimination of special causes, and improvement of a process is accomplished through the reduction of the common causes. That means common causes actually are a part of the system. So the variability caused by special or assignable causes is something that is not inherent in the process. That means for the time being it has happened, but if you take some remedial action, obviously this cause will be eliminated, and that the process has become free of this particular clause. Deming believes that 15% of all problems are due to special causes. Now I'll just will take 2 to 3 minutes of time, two more minutes to explain the common causes. The variability due to common or chance causes is something inherent to a process. That means you are living with this. So any systems we are talking about, that means that we try to reduce the variation, but there will be some variation. So at any point in time you must know that what is this allowable variation, and this variation is due to the common causes. So this is the meaning, and the process operating under a stable system of common causes is said to be in statistical control. We will be using this term, it is referred to as the statistical control or not. So management alone is responsible for common cause, that is a part of the systems, as the management has created the system, and Deming believed that about 85% of all problems are due to common causes and hence can be solved by action on the part of management. This is through his study he concludes. Okay, so here I conclude. So later on we will discuss on the common causes of variation as well as the assignable causes of variation. So if you can remove the assignable causes, the process becomes in control state, and if you can consider the common causes, and you can eliminate some of the common causes, we say that the process, the quality control system has improved.